Welcome to the Computer Science and Engineering Colloquium. We have today Thomas Leung, who is a job applicant. He did his undergraduate work at Caltech, where he started doing computer vision research in face recognition. And he is getting his PhD from Berkeley, where he works with Jitendra Malik. And he's done work in segmentation, object recognition, texture analysis, and texture synthesis. And he'll be talking today about object recognition with both material and shape.
Okay, thank you, Linda. Good afternoon, everyone. And I'm Thomas. And one of my main interests in computer vision is to do object recognition. And today I'll talk about two different aspects of it using different sources of information. But first of all, what is recognition? If I show you this image, all of you can see right away that this is Mona Lisa, even though the graduate students probably haven't seen the real one. But now, I show you this image. No. Can anyone tell me who he is? No. Okay. I have no idea either. But the point here is that even though you don't know who this guy is, and even though he's making a funny expression, you can still recognize that this is a face without any problems. This is a male as well. And similarly, for these two cars, they have different shapes, they have different colors, they have different models, they have different makes, and you can still recognize that they are cars. So one of the aspects of recognition that I want to point to you is that you can recognize specific instances, say Mona Lisa, or object classes, say faces. And you can also recognize, say, a beetle versus the object class cars. And humans can do this really well. And we can also do object recognition despite change in illumination. Now the light is turned down and you can still recognize my face. And also, if I turn my face a little bit, you can still recognize that it's me, and change in expressions, occlusions as well. And I can demonstrate this through these images. Some of you may recognize that this is David Mumford. And here are 12 different images of him taken at different illuminations. I think maybe except for this one, and there's probably not this one either. You can all recognize that these images come from the same person. So we as humans, we can recognize objects despite a lot of change in illumination as well. And what are the applications of recognition? So one of them, which is in terms of security or biometrics, is recognizing fingerprints, recognizing iris, recognizing faces. And other applications can be human-computer interface. If you can recognize certain gestures, certain motion, you can have the computer do something automatically. And the more traditional application of object recognition is in target detection. Say the army wants to find all the enemy tanks so that they can shoot them. Or nowadays, in a more commercial application would be content-based image or video retrieval. You want to find all images of Bill Clinton hugging Monica Lewinsky on the web, or something like that. So what are the sources of information that allow us to do object recognition? So one of them is shape or geometry. I'm going to use these two terms interchangeably. So you can recognize that the top object, the top picture, is a football, and the bottom one is a basketball, purely because of the shape of the objects. The football is elliptical and the basketball is round. But what about these two guys? So the top one is a golf ball, the bottom one is a ping pong ball. The shape is the same, they're both spheres. Color is the same, they're both round. What enables us to recognize that they're different? It's probably because of the material it's probably because of the material the golf ball and the ping pong balls are made of. The golf ball is more shiny, and you also have these little dips or the textures on the surface. For the ping pong ball, it's more dull, and it doesn't have any texture or pattern on the surface. So the other source of information is what I call material or texture. Again, I'm going to use these two terms interchangeably. So the outline of the talk is the following. First, I'm going to talk about texture or material. I'm not going to give a precise mathematical definition of texture, but I will show you enough examples of texture so you know what I mean. I'll talk about different aspects of texture, detecting them, synthesizing them, modeling them, learning and recognizing them. And the second part of my talk, I'll talk about geometry and shape. I'll give you one definition of shape that I'm going to use, and I'll talk about different aspects of shape recognition, shape classes, modeling of shape, and recognizing shape. So what is texture? If I say texture, the first thing that probably came to your mind is something which is repeating. Say on the left here is one of those Windows background. What you actually have is one particular pattern here which is tiled up all over the surface. And other examples of these kind of repeating texture or repeating notion of texture is a brick wall. You have one precise element of a brick, and then you tile them in some way all over the surface. But this notion of repeatedness does not always guarantee same appearance all over the surface. Suppose in this building, the windows are actually repeating all over the surface, but since the surface is slanted, the appearance changes. But visually, we still see that as one coherent piece of texture. So the analysis of texture has to deal with that. And similarly for the patterns on the shirt on your right-hand side. So I said texture is something which is repeating, but it's not always the case. On the left here is just a white noise pattern. Visually, it's texture as well. But you cannot talk about any prototypical elements which is repeating on the surface. So there's some notion of stochasticity there's some notion of stochasticity for texture. And on the right is an image of a piece of bread. You can somewhat say there is some elements repeating, say these little bumps, but they are not repeating precisely. So again, there's some randomness on it. So for all the images I show you, you can pretty much think of the texture as some paint pattern or some albedo change on the surface, but it is not always the case. Say, visually, these two images, they look like texture to us, but physically, on the left are some flowers sticking out of the surface. And because of this 3D nature of the surface, you don't see as much yellow blobs here, and you see a lot more yellow here. So this is because of the occlusion effect of this type of what we call it non-tangential texture. And also for these like image of soldiers. So if we want to capture all different types of texture, we need to take into account these images where the elements are not lying on the surface. And if you change the illumination of some of these materials or these textures, these are actually two different textures taken from the Columbia-Utrecht database. What they had is they have a lot of different materials, and they take images of them at different illumination, different viewpoint. What you notice is that because the material is not paint on the surface, if you change illumination, you see more shadows here, you don't see as much shadow here, and you see the specularity on the top image, and you don't see as much specularity here. Same for these material. So if we want to have a general or a good model for texture, these type of aspects these types of aspects have to be taken care of. So the different things about texture I'm going to talk about is, first of all, I'll talk about detection of texture or shape recovery. And I'll talk about synthesis, I'll talk about building a physical model for texture. At the end, I'll talk about learning and recognizing texture. I'll spend more of my time talking about synthesis and learning and recognition because these are the more recent work that I did. And for the rest, I'll just go through it pretty fast. Okay? So now, if we assume texture is made up of some repeating elements, there is a distinctive element repeating on the surface. What you can do is that you can actually find these distinctive elements automatically, and you can group them all over the surface, even though these elements, they're actually changing the shape, changing the appearance along the surface. And given these correspondences between elements, like this element corresponds to that guy, and all over the surface, given these correspondences, you can recover the surface shape, such as the surface slant, the surface tilt, the curvature, and everything. And if you're interested in this work, you can go to my webpage and see one of the papers. I'm not going to spend too much time on it. So now I spend more time on talking about synthesizing texture. So for texture synthesis, can we use this notion of repeatedness of texture to do texture synthesis? So the immediate answer is, okay, let's try to tile them. However, real-world textures, they span a whole spectrum. This is more repeated, this is more stochastic. This, as I said before, may be somewhat in between. So we need a model that can capture these things all together. So some of the previous work on texture synthesis, they basically follow two main categories. One of them is you analyze texture by computing some wavelet statistics. Say you can compute the first order wavelet statistics, second order or high orders, and then try to match or try to change an image of random noise to have the same statistics and synthesize the texture in that way. And these are the examples that people have tried. And the other direction or the other aspect or the other type of texture synthesis is to forget about all those wavelet statistics. Do it directly on pixels. And Popat and Picard is one example of that. The work I'm going to present here follows more in the pixel-based matching paradigm. So the motivation of our approach actually came from text processing or text modeling. Shannon in 1948, he proposed a way to generate English-looking text using what is known as n-grams. So an n-gram is basically a generalized Markov model. And given the n-1 previous words, the next word is determined by a conditional probability distribution. Of course, you can learn this probability distribution, or you can just tabulate them to form a huge table. But you can also sample this Markov chain to generate new words. I'll demonstrate one example here. Okay, suppose you have a huge book, and you want to synthesize some text or some sentences that look like they're coming from this book. You open the book randomly, and you pick out two words. And these two words can be "we need." And then you close the book, open it again randomly, start reading from a random place. And you continue on reading until you hit the two words "we need." And then you copy down the next word. And you continue on the process, and you can generate sentences like this. And I think in the 1960s, someone in Biolab, they actually wrote a program like this to synthesize English-looking text. And the book that I said before, what they used is the odd.singles corpus. And here are some sentences that they synthesized or they generated. I'll pause for 10 seconds. Okay.
What was the window size? Was it 2 words?
I think it's 2 words. Mm-hmm. Okay, so what you observe here is that the local structures are well preserved. If you look locally in like a 3-word window, they all make sense. But the overall sentence doesn't make sense. That's why you guys were laughing. And so, because of the success of this text synthesis, can we use a similar model to synthesize texture? One hypothesis that we are trying to get at is, for texture, if you can capture the local structures well, the texture is appealing already. So let's see if we can do it. So the thing I have to tell you about is, what's the definition of Markov property in 2D? So the thing we define it is, suppose you're given a window and you want to know the intensity of this pixel in the middle, and you have already synthesized everything on the outside. So the way you go about it is, and the book, the analogy of the book that I mentioned is the example texture you give me. You give me a piece of carpet and you want more of it. The piece of carpet you give me is the book that I have to go through, I have to look at. So you basically look at this window, and for the given, or for the synthesized pixels already, you look over in your book and see if you have things which match to it, or which are close enough. And then you copy over the pixel from these windows over, and you can synthesize texture in that way. So here are some examples of Brodach's texture that are synthesized On the left is the left teeny image is the patch that you give me, is the example you give me. And the right are the textures that I generated. Okay.
Can you say briefly how that work you just described is different from the previous work that you mentioned that was similar?
The Popper and Picard?
Exactly, yeah.
Okay. So their work is, they try to do some quantization on like local windows. And they try to build an explicit probability table. And because of that quantization, you don't get as appealing a texture as we can. And we ignore that quantization, we ignore that probability table. We do a sampling method. So that's why we get much better results. Well, I won't say much better, but at least they're pretty good. But the recent work by the people at Stanford, they are somewhat in between Popper and Picard and our work. Like, I think it's Mark Levoy and one of his students. They have a texture synthesis paper in SIGGRAPH. There's something in between our two approaches. Okay. So you probably didn't notice one thing. If you look at these two wires, they're wrong. So the original image, all the wires are interleaving. But these two, they are above this wire at the same time, below them at the same time, above at the same time. So the reason I'm pointing this out to you is that, like I said before, texture, if you can capture the local properties pretty well, you get the visual appeal or the visual notion of texture. And here, globally, these two wires, they are wrong. But visually, you don't see the difference. So here are some examples in color. And since Shannon motivated our work, and we took a clip from the New York Times and tried to synthesize texture based on this example. And now we are treating this patch of text as an image. There's no notion of characters or letters. And here is an example synthesized when you allow a higher degree of randomness. And here you allow a small degree of randomness. And you probably don't see much difference between these two images unless you try to read them. Okay, so David, one of the reasons why we can synthesize this good results is we don't do any quantization. So we just do sampling and the results are better. So you can also do constrained text synthesis. You have this as your original patch and you want to fill out the border. And here are two, the top is one example, the bottom is one other example. In the middle, the borders are filled with texture which are more random. And on the right are filled with texture which are still well structured. But one thing to notice is that even for this filling in with more random texture, you don't see so much of a border effect around, say here. And you definitely don't see any border effect around this edge. So this is one thing you can think of when this is like the main, or one of the applications for this is, say in computer graphics, I put my hand on top of some texture in the background, on top of a brick wall, and you want to remove my hand. Then what you have to do is to fill in the texture and beneath my hand. So this is one possibility that can be done. So far, what I have done is that I'm treating texture as repeating 2D patterns. I'm treating it as some paint on a surface. And like I mentioned before, all those flowers in the field, soldiers in the field, or even the little dimps on the golf ball, I ignored those height variation. And now I want to capture them. So the first direction I try to address those is to build a physical models. I try to model the surface explicitly, and then I can derive something relating to visibility and shadowing effects. So some of the previous work of trying to build analytical models for texture, or analytical models for what we call a 3D texture. 3D texture meaning there is height distribution on the surface. So examples include a particle volume by Kajir and Kay. They used this model to render animal fur pretty well. And other examples are Gaussian bumps of Lambertian reflectance, which are more recent work by Kundrik and the Columbia group headed by Shinaya. And of course, there are the traditional or more traditional graphics models, such as bump maps and displacement maps. So these are the type of images, or these are the type of textures that I want to model. Like I said before, if you look closer here, the amount of yellow pixels is not as high as over there near the horizon. This is why I put up the title, why do we see more flowers in the distance? If you look here, you look near your foot, you look near your feet, you don't see as many yellow pixels. If you look in the distance, there seems to be more yellow flowers because the density of yellowish is higher. So the model we build is that each of the elements are cylinders, and there is a color distribution along the cylinder, just like one of these. And these cylinders are distributed all over the surface through a random process. And here are two realizations of them, one on a planar surface, another on a spherical surface. So one thing you notice at first, right away, is that if you look around here, the density of red pixels versus the density of red pixels around there is much lower here, just like the image here, or the real image on the left. So this looks like a nice example, a nice image to synthesize. But because of this analytical model, we can derive explicit relationships relating, say, visibility of yellow pixels with respect to slant of the viewing angle, or with respect to density of these elements. And using these expressions that we got, we can also recover surface shape. We can understand how the density of yellow pixels relate to crowdedness of these elements, relate to the surface shape and stuff. And one example that I show you here is that on this image, let's concentrate on this white rectangle. I hope you can see it at the back. These little dots up here, they are the density of yellow pixels in this white rectangle. And this curve is what our model can predict. And using the model that we have, you can also derive the slant or the surface shape of this little, or of this plane, which says it's about 70 degrees of slant, which is reasonable. And you can also do the same thing for curved surfaces by relating the curvature of the surface and slant and tilt and everything to the amount of yellow pixels you see. Okay, this is nice and fine, but you may want to ask, how useful is the model? The answer is, it's not that useful. So if I give you all these images and ask, can you use the model I proposed to apply to all of these? The answer is definitely no, because none of these are actually containing cylinders on top of a surface with some color variation. So how can we deal with this? There are basically two different approaches or two philosophies to model texture or to do modeling in general. So one of them is you build an analytical model for the texture. The advantage, like one of the examples is like the one I had before. You have cylinders on top of surface with color distributions along the height. So what the advantage of this analytical model is, it gives you intuition to the problem. From the model I built earlier, I can relate surface shape to visibility to shadowing. But it's a restrictive model. It doesn't apply everywhere. So the other direction you can go is you just give me a lot of images and I don't try to build a physical model. What I do is I try to learn a model from the images. What's the advantage of that? It's a general model. It can be used everywhere. Well, it can be used everywhere for all those textures which you have shown me. However, it's not intuitive. You cannot relate any of the surface shape to what you see in the image, or you cannot relate any relationship, say, illumination direction, surface shape, or density of the elements to what you see in the image. So there are goods and bads for both methods. But I mentioned one particular way to do analytical models, and now I try to go the other direction of learning a model from images. Okay? So the main hypothesis that we are trying to push for is that for different textures or different materials, even though the appearance are different, the appearances of different materials are different, we are trying to hypothesize that all of them are made up of elements from a universal vocabulary of tiny prototypical elements. These elements can be ridges, bumps, shadows, paint, We call these 3D textons. So in short, what I mean is all surfaces, you can think of them as a collection of alphabets. These alphabets can correspond to different physical structures, like a bump, a ridge, or they can correspond to some specific paint pattern, like paint of a cross or something like that. So for people who are familiar with speech, what I mean by these 3D textons is they are analogous to phonemes in speech processing, or you can think about them as alphabets in English. So all English documents are basically made up of the same 26 alphabets. And now I'm saying all surfaces, all textures, they are made up of the same set of alphabets. And I will try to tell you how I find these alphabets and how many are there. So more details. So what do I want these 3D textons to capture? I want them to capture both geometric effects, say little bumps, little ridges, shadows, or grooves, or holes. But I also want them to capture photometric effect. Suppose I have some paint on the surface. I also want these 3D textons to capture them. And okay, let me try to point, well, okay, let me do that later. So the way we represent each texton is by a collection of image patches. Say if the way I represent a little bump is I represent it by a picture illuminated this way, I represent it by another picture illuminated this way, I represent it by another picture illuminated this way. So it's a collection of pictures or a collection of image patches to describe each texton. And I'll try to show how to learn this texton vocabulary from images. Okay, the way to test, so there should be a way to test how good the vocabulary I learned is. Otherwise, I'm just talking. And the way we do it is to try to use this vocabulary to do recognition or to do synthesis. And I will say more about what I mean exactly by those. So now you give me a bunch of images. They're shown here. This is crumpled paper, this is concrete. For each one of the images, you give me a lot of examples, a different illumination, different viewpoint, different things. And you give me a lot of different materials. So the first step that we do is to analyze it by a set of wavelets, which is pretty standard for texture discrimination or texture analysis. And then I will go through a learning phase where I take these wavelet responses and try to learn the particular textons that I have. Let me elaborate a little bit here. Let's think about the reason why I need so many images for one single material. So think about a little bump versus a painting of a bump. If I give you one single image at one particular illumination, they will be exactly the same, because I can always paint my bump exactly like what it is out there in the physical world. But what happens if I change illumination? If you change illumination, the bump will change its appearance. But for the painted bump, it will almost look exactly the same. Or on the other hand, think about a ridge which casts a shadow on the surface versus a painting of a shadow. If you change the illumination of the shadow, if you change the illumination in both cases, one from here to here, if you have the shadow, the real shadow, it will change to the totally different direction or different side of the ridge. But for the painted shadow, the direction or the location of the shadow edge will always be the same. So if I give you only one image, you cannot tell me locally what it is. Is it a bump? Is it a ridge? Is it a paint? You cannot do that. But if I give you a collection of different images, different illuminations, and different viewpoints, you can do that, because the difference will show up. And the particular learning algorithm I used here is a simple vector quantization, which I use a k-means algorithm. Yeah.
So you feed in the illumination and the viewpoint as well to the analysis stage?
So here I assume I know the illumination, I know the viewpoint in all these images, and they are all registered. So like the first pixel here corresponds to the first pixel here, corresponds to the first pixel there. So I know exactly how each pixel changes its appearance with respect to viewpoint, with respect to illumination. And here are some examples of the textons that I hope I will get out. So on the top, you can think about this as a little deep hole, because if you change illumination, it remains dark everywhere all the time. It has to be a deep hole because no light goes in, no light comes out. And you can think about this as a little ridge. This is actually the shadow, because if you change the illumination, the width of the shadow actually gets wider. But a priori, I never forced my learning algorithm to come up with these things. All I can do is to hope that it will come out something like this. And the only way to test it is to see if I can use this vocabulary that I learned to do recognition and synthesis. Yeah?
So the learning that you're doing is clustering in a space where each well-lit coefficient is one of the dimensions?
Okay, so the learning I'm doing here is basically clustering, and the dimension is the number of illuminations, the number of images here multiplied by the number of filters I use here. Suppose I have 20 filters here, and for each image, for each texture, I give you 20 images at different illumination, then the dimension is 400. So you're doing clustering in a 400-dimensional space.
Which is extremely high.
Yeah, and it takes a long time.
And you need a lot of examples.
The number of materials I used are 20, and the number of images I used are 20.
And how do you determine the number of clusters?
Okay, so, okay, I'm trying to see if I should say it here. Okay, the number of, okay, let me say it this way. For the problem of recognition, I tried 100 clusters, I tried 200 clusters, 400, 800 of them. And there is not a significant difference in performance between them. So I stick to 100. And for the problem of synthesis, I used 2000 because I want to reduce the quantization effect. Because basically, the learning here I'm doing is just vector quantization. If you quantize it too much, you have some artifacts based on that. So once you have this texton vocabulary, what you do is, if you give me an image, I can mark each of the pixels to the corresponding texton. So if this is a shadow or this is a groove, I will try to match it to the texton which is most similar in appearance. So if you look along here, they all get mapped into the same texton shown here by the same color. So this is the representation I have for each of the materials. Okay, one thing I have to point out here first is that, like I said before, if you just give me one image and locally I cannot determine what it is. It can be a bump, it can be a paint pattern, it can be a lot of different things. So if you give me one image, doing this is difficult. And right now, assume you give me several images here. So I know exactly locally whether one is a bump, one is a ridge, or one is a shadow. And I can map them into the texton representation. So once we have this texton representation, we can do two things. First, we can ignore spatial arrangement and use histograms. This is analogous to ways of comparing documents. There are people who compare documents by just looking at the histogram of the count of words. Say they have a document, they count the number of words, material in the document, they count the number of words, arrangement in the document, and they keep a big histogram for each of the materials, for each of the documents. And at the end, they compare these histograms. If the histograms are similar enough, they say these two documents are similar. If the histograms are far apart, if the histograms are quite different, they say these two documents are quite different. And that kind of method is reasonable. People have some success in document retrieval. But on the other hand, you can also keep the exact spatial arrangement of the texture. Say you can always, if you ignore the spatial arrangement and use histograms, you can never be sure that, or you don't have the information saying a ridge is always next to a bump. Maybe for a particular material, particular texture, a ridge is always next to a bump. If you ignore the spatial arrangement, that information is lost. But of course, if you want to have more if you want to have a better representation, you should keep the spatial arrangement. And I will show you two applications. One is in terms of material recognition, I ignore the spatial arrangement and use histograms. And for synthesis, I will keep the exact spatial arrangement, and I'll show you results in both cases. So here are two of the histograms. Here are two histograms for two different materials. One of them, the top is rough plastic, the bottom is pebbles. And these are histograms, and if this, I don't know, if this texton correspond to ridges, what this means is that rough plastic has a lot more ridges than pebbles. But I don't know what each of the textons correspond because they are learned. And the way to tell differences between histograms is by using a standard chi-square difference. Oh, so here is the similarity matrix between different materials. And the ideal case you want to get is a 1 on the diagonal and 0 everywhere else. This is pretty much the case except here. Okay, in case you cannot read it, this is 1, 0.7, 0.8, and 1. So what this means is that our recognition system is quite confused between the two different types of plaster, plaster A and plaster B. But if you look at the real images of the two different plasters, they indeed look quite similar. So we are satisfied with the performance here, meaning the algorithm is kind of like capturing the visual aspect of different materials. And in all our database, there's nothing like aluminum foil, which is really shiny and specular. So you would expect a strong 1 here and almost 0 everywhere else. And this is pretty much the case. So in some sense, this is doing reasonable thing. So now, if you only have, so now let's look at the problem of recognition from a single image. You have a database of different textures. And for each one of them, you have 3 different images. 3 images illuminated at different direction. And you have maybe 20 different materials. And now you give me a single. I want to emphasize that you only give me one single image of one of the materials, and it's illuminated differently. Not any one of these 3 illuminations. And you want to tell me, and you want to tell what material this is. This is similar to the face recognition problem. Suppose you have seen me under normal illumination, and suddenly I give you an image of me illuminated strongly sideways, and you want to recognize, or you want to tell whether it is me or not. So the main problem here is that, it's like what I said before, if you give me only one image, I cannot label it to the texton histograms, because locally, I cannot say whether it is a bump or a paint or ridges or anything. So how do we do that? So it is difficult, like I said, it's difficult to label image with a single image. However, if you know what material you're looking at, suppose you know you are looking at my tie, and there are no bumps, no ridges, nothing like that. Everything is just paint. So you can guess the labels, you can guess the local texton label easily. On the other hand, if you know the labels, the texton label on the material, you can guess the ID by basically matching the histogram. So this chicken and egg problem suggests some expectation maximization type algorithm, and we use the particular one, a Markov chain Monte Carlo method. I am going to skip all the details on this, and I'll show you results directly. So here is, oh, I apologize for the poor quality. So this, what I'm showing here is a receiver operating characteristic curve. What it is on the y-axis is the probability of detection, and the x-axis is the probability of false alarm. So the ideal recognition would be at this corner where you have 100% detection, no false alarm. And here what I'm showing are different curves for the performance when you trade off detection versus false alarm. And the different curves correspond to different novel illuminations. If you take the average of them and do the equi-probability point, what you get out is something like 85% detection versus 15% false alarm. Okay? So to do synthesis, If you give me one image or several of them, I can map them into the Texton labels. But what is good about the Textons is that each one of them tell me how it appears when you change the illumination. So you can basically change the illumination of the image, or you can change the appearance of the image easily. So here are some examples. In the middle column is the ground truth. On the right-hand side is what our model can produce. On the left-hand side is the traditional texture mapping technique, where you assume numbers surface, flat numbers surface. Yeah, that's it. So, and here are two different materials. What you notice is that we can capture the shadows and the highlights or the specularities pretty well. I think right here, because of the projector, you don't see much of the artifacts, but they are there, trust me. Okay. So here are examples in color. Pay attention to the shadows and the highlights and stuff. So I spent 45 minutes talking about texture and material. I better move on to the second part, which is talk about shape and geometry recognition. So, well, I said that before. I give you this image. It's a random, not so random collection of facial features. And I hope what you see are two faces. Okay? So there are three things I want to point out. One of them is, even if I just show you a collection of specific features, you can still have a percept of a face already. I mean, at least that's what I hope you have. Okay? You have a percept of a face already. And the second thing I want to point out is that in this example, the nose is missing. But for us, we don't have much difficulty perceiving that this is a face. So for humans, we are quite robust in terms of occlusions or missing features. So we might also want a computer vision algorithm to be able to deal with that. And the third thing is, if you compare these two faces, the shape or the configuration of these features are quite different. This is more elongated, and this is more roundish. So if we want to recognize objects, these kind of variations we need to take into account. And now I show you this image, and I hope you don't see any faces here, because the arrangements are random. Okay, no one sees faces here, right? Okay, good. So now, what our shape model is composed of is that all objects are made up of characteristic features. For the human face, it can be the eyes, the nose, the mouth, etc., etc. For cars, it can be license plates, it can be headlights, it can be the top of the hood, etc., etc. And objects are defined by a collection or a configuration of features. And object classes, say the object class of a face where the exact configuration can change, object classes basically mean the configurations can change from instance to instance. So let's take one step back and ask the question, what is shape? I said way in the beginning that I'm going to use geometry and shape interchangeably. So in geometry, what people mean by geometry is that two objects are the same up to a certain group of transformation. In high school or grade school, when you learn that two triangles are congruent, it basically means you can rotate, you can translate one triangle, and it will lie exactly on top of each other. So the particular group of transformation when you learn geometry in grade school is the Euclidean group of transformation. So now in statistics, what people try to do is they want to capture a distribution, a variations in this notion of shape. And the particular group of transformation that they're interested in is the Euclidean group of transformation, because the problems they usually look at are, say, a 2D pictures of hands, and they want to see how the shape of hands change across geography or across time. And that's the type of thing they look at. But in computer vision, all objects live in a 3D world. The set of possible transformations is not just the Euclidean group. It's basically all camera projections, because everything lives in a 3D world. The way we get access to them are through photographs or through videos. So there's a projection involved. So in vision, what we want is we want to build a probability distribution on shape where the transformations are all camera projections. And I'm not going to use all possible camera projections. I'm going to restrict my attention only to planar objects. And the size of the object is, the distance of the object from the camera is big compared to the focal length of the camera. So camera projections can be modeled pretty well by affine transforms. And affine transforms have 6 parameters. This A is a 2x2 matrix, and this is the translational component. And you can think about an affine transform as having 4 different components: translation, rotation, scaling, and shearing. So how do we capture the shape of objects invariant to affine transforms or invariant to all camera projections, which are modeled by affine transforms? Suppose you have some features in the 3D world. Say these are my eyes, nose, and mouth corners. And here are the coordinates of them. Because I'm talking about planar objects, so my coordinates has only x and y component. And there are, because of different people have different shape, so this x, they follow a particular probability distribution. And now I want to move these coordinates or these components so that they're invariant to affine transform. The easiest way is to just look at them. I mean, this is well known in geometry, in vision. The easiest way to look at them is to map them into an affine basis. So you map these 3 features into a standard coordinate, and the coordinates of the remaining 2 features represented in this affine basis would be affine invariant, and I represent them by, this is an equal sign, not minus. I represent them by this 4-dimensional vector. So the question now becomes, there is a distribution over this space because different people have different shapes, or different objects have different shapes. Because like when I'm talking about human faces, because the shape of my features will be different from the shape of your features and things like that. So there will be a distribution over here. The question becomes, how does this distribution translate into the distribution over in these variables? So if you assume that the x, or if you assume that these coordinates follow a joint Gaussian distribution, which is shown here, and if you work hard enough on the math, you will get the distribution of the shape variables in this format. This is this guy over that, And one thing you may complain is that a single Gaussian distribution is too restrictive. So you can talk about a mixture of Gaussians, and what you get out is just a mixture of these shape densities. So here are 2 examples of the shape densities. Suppose, let's focus on the top. Well, let me skip this. The quality is too bad. Okay, the thing we use to do this shape theory is to do view invariant face detection. The problem is the following. You give me an image, and I have to tell you whether there is a face in the image. If there is one, I have to tell you where exactly it is. So we use 5 different features: 2 eyes, nose, and 2 mouth corners. And what we achieve is something like 86% detection in an interesting face database. I will say, in the interesting face database. And the nice features here is that it can handle occlusions and rotation in depth pretty well. So if you just look at the number 86%, it sounds pretty bad because people in MIT, people in CMU, they can do something like 97% or 98%. But the problem that they have, the problem that they have is their systems can only detect frontal faces. If I turn my face, say, to the side by 10 degrees, it usually fails. So the interesting fact for us is that we can recognize both rotation in depth and also occlusions. Also for the MIT or CMU systems, if you put your hand in front of the face, occluding the eye, they will have a miserable time trying to find the face. So here are some examples of face. Here are some examples of the face detection results. These are 2 toy examples, and these are to demonstrate that we can do well when the face is rotated in depth. Okay, so, well, this is a summary of what I have talked about. I spent most of my time talking about modeling texture, recognizing texture, synthesizing texture, and near the end, I talk about a particular model of capturing shape classes, and I apply it to view invariant face detection. So here are the references of the things I talk about. I didn't have the time to mention some of the work that I have been doing recently on image segmentation. The main reason I was looking into image segmentation was that, like, for all the results or all the work I show you on texture synthesis, texture recognition, texture analysis, there is a nicely cropped piece of texture. But if you give me a real image, how do I achieve that? Or how do I get at a nicely cropped piece of texture? Image segmentation is one way to go. And on the bottom is my web page. You can see, you can download the papers or see more details there. So in terms of future work, there are 2 main directions of future work. One, the top 3 bullets are more from a vision point of view. The bottom one is from a computer graphics point of view. So since I've been looking into image segmentation, there's one rather useful or interesting thing to look at is the relationship between low-level vision and high-level recognition. Say, it is rather obvious. Well, I don't know. To me, it's pretty obvious that low-level segmentation can help recognition, but there are quite a bit of studies, especially in the psychophysical literature, that says that recognition can affect low-level segmentation. Suppose you can recognize that this is a face in the image right in the beginning. A lot of the segmentation, a lot of the stereo analysis you do can be totally wrong. So one interesting thing is to look at the relationships between the 2. And in this talk, I mentioned material or texture recognition and shape recognition, but I was treating them as 2 totally independent pieces of work. And the best, or one of the nicest thing to do is to try to combine them. Say, if you want to recognize a tiger, the best thing to talk about or to describe a tiger is it has some orange and black stripe texture, and it has a cat-like shape. So to use both of them together should definitely be useful. And at the end, I want to go into more of the motion analysis. I want to do some work in terms of recognizing human motion, recognizing gestures, and that's something interesting. In terms of computer graphics, what I want to do is, so when I was talking about the texture synthesis or 2 pieces of texture synthesis, one is synthesizing texture as 2D patterns. The other is synthesizing texture when you change illumination. So one thing I'm interested in is to try to have models of all sorts of different materials. The model that I showed, like the 3D Texton model, is okay, but there are still quite a bit of improvements that can be made. So things that I want to do is to change viewpoint, change illumination, and also talk about I want to do something in changing geometry, changing topology. If you give me a piece of carpet on the floor, I want to map this carpet into a sphere, and also when I change illumination, I want it to look correctly. So here are my fundings and my collaborators. Half of them are from Berkeley, half of them are from Caltech. So, and this is it. Thank you.